Hey everybody, welcome back. This is episode 6. Today we're going to talk about parallel circuits. Now I'd recommend if you have not already watched the series Circuits, which was episode 5, it's probably a good idea to go back and at least skim through that one. The discussion that we had in that video was taking a little bit of a deviation away from the normal way that the series circuits are presented in a textbook or tutorial. And I want to make sure that when reading that or listening to that video, you don't walk away feeling like I'm like I have a bad opinion of the way that it's presented, because that's definitely not true. Those are absolutely legitimate circuits. There's nothing wrong with them, but they tend to only present half the story. And the problem is they always present the one half of the story, which is the series devices put in the load devices, which are in series with each other. They very rarely cover control devices in series. But depending on your context, which my background is mostly industrial control systems, I've done a lot of work with small scale control systems too. So things like op-amp circuits and all kinds of breadboarded circuits, microcontroller things. I've done lots of work with those. So I understand the context that it has there. But since my background is primarily industrial, I tend to look at things through sort of that lens, where I say, okay, does this really represent the way I'm going to see something in real life? Because it's easy to look at a textbook and finish all the questions that are in the back of the chapters, and they can be real easy, real difficult, but they're all mathematically based and trying to get you to understand the concepts of the series load devices, which is fine. But we also can't ignore the other, if it's more common, series control devices, and we don't want to risk losing our entire perspective just because we're focusing on one of those too much. So it's not to say that the load devices are wrong and focusing on load devices is the bad way to go about presenting circuits, but it's only half the picture. So that's why I emphasize the control devices so much in the series section. Now that we're talking about parallel, I'm going to sort of do the same thing. However, it is much more common to see parallel circuits applied to both loads and controls when we're in an industrial setting. In a small scale circuit setting, like when you see things in a textbook or little printed circuit boards that have components soldered into them, breadboarded circuits, those kind of things you're very likely to see parallel loads and parallel controls. Extremely common. In fact, when we talk about transistor-based devices, it's very common to have a parallel circuit, because in a transistor, there's one leg that's the same on the transistors. And if that's a small bipolar junction transistor, then it's going to be the emitter pin that's common between the collector and the base. On field effect transistors, other types of AC control devices, which are called thyristors, there's always some sort of common connection between the control side and the load side. The transistor is just the thing that puts the two together. But one of those is a common connection, meaning that power must be flowing into one place from two different lines to be sent back through one. That means it's a parallel connection. So we'll be able to discuss this equally as both control devices and load devices, pretty much regardless of what our context is. Although probably I'm going to keep things a little bit more focused on industrial devices, because again, that's not only what my background is, but also, again, when you look at all these textbook examples, they never really focus on the industrial devices. They're more concerned with the small scale circuit devices. So to kind of fill that gap, that's why I emphasize the industrial stuff a little bit more here. And industrial goes along with residential. Now, which of all these scenarios are you more likely to experience on a day-to-day basis? The outlets in your house or printed circuit board repair? I would say probably the circuits in your house. The outlets, the light switches, those kind of things are probably something that you deal with on a more regular basis than any other scenario. So we can't exclude those from our discussion. Now, in a house, it would be safe to say that nearly everything is connected in parallel. And how do we know this? How do we look at a scenario and say, how do I tell whether these things are in parallel or in series without having a schematic? There may be some modern houses where they provide you with an electrical diagram, an electrical schematic of the house, but it's probably not very common. Most likely, you're probably going to be looking at a house that's fairly old. You're going to be looking at wiring. You open up the front of a box, whether it's a light switch box or a junction box inside your house, and all you see are wires. No diagrams, no prints, no schematics, nothing. How do you determine whether something is in parallel? Well, first, let's look at the load devices here. The way I would instantly be able to tell whether load devices are connected in parallel is if they're being fed with a 120 volt source and there's 120 volts printed on the load device. If that is the case, you know that every one of those load devices must be getting the full source voltage. If the load device is getting the full source voltage, then there's only two possibilities. And one, it's the only load device in the entire house, or they're all getting the same voltage. They're all getting the full source voltage that they need. Those are the only two possibilities. So if your light bulb, if you look at your light bulb that you take out of the light socket, it says 120 volts on it, and the panel in a residential setting, it's all 120. Same thing in an industrial setting. You look at your power supply in there and you see a 24 volt DC power supply. And you look at one of the lights and an indicator light says 24 VDC. So you know that the load devices must be getting the full source voltage. So here again, two possibilities. It is the only load device in the whole circuit. Or all of the load devices must be getting the full source voltage. Now, from everything that we looked at in the series load devices, if you put two resistors in series with each other, neither one of them is going to get the full source voltage. So if they're all getting the source voltage, we know they can't be in series. They must be in parallel. And that's the whole point of industrial circuits. We want them all to get the full source voltage, and we want to be able to run more than one thing. You press a start button, and it runs more than one device, maybe a relay and a light. In your house, you flip a light switch, and that light outlet probably, or that light fixture, might have 2 or 3, 4 bulbs in it. Well, you want them all to turn on when you turn on the switch. Maybe there's 4 or 5 different fixtures with 4 or 5 different lights. That could be a lot of load devices all on one circuit. But as soon as you flip the switch, the control device, all of the load devices get an equal voltage, and not only is it equal, it's equal to the source voltage. Those spell out the exact scenario for what a parallel circuit accomplishes. The full source voltage applied to all load devices in parallel with each other. And a good symptom, or a good sign, an indicator that things are in parallel with each other, can be a couple of different things. Focusing on the residential and industrial again, on a printed circuit board, those are a little tougher. Sometimes it's not as straightforward. You can't always look at one of those little green circuit boards with tons of components on it. And even trying to follow the wire traces, they've got some of those boards that have layers, just tons of layers buried down inside, and wires can be connecting or crossing over each other inside the board. If you were to zoom in and take like little layers off of it, those are very difficult to just look at and tell. Without a schematic, it is nearly impossible to really tell exactly how a PCB is laid out. So we're going to kind of ignore those and say, if you really want to learn how to diagnose those and repair those, that's a whole different story in itself. But residential and industrial is definitely worth knowing about. I would say residential is at least worth having some handy knowledge on, because you can do a lot of work in your own house and save yourself a ton of money just by understanding a little bit about how these things work. But again, an indicator of how parallel circuit, or what shows us that their parallel circuit is present. The first sign is in a residential setting, you see wire nuts. Now, a wire nut inside of a junction box is the little wing nut thing. You screw it onto the top of wires, and it twists the wires and binds them together. If there are only 2 wires inside of a wire nut, then that means you are simply extending the wire. Because that wire that used to just have a stripped off end on it is now being continued another length, and that's not a parallel circuit. If you, however, see 3 wires underneath it, so 3 wires all together, and then a wire nut twisted over the top of all 3 wires, or more, so it could be 4 wires, although it's not common to see 4, 5, 6 wires all under a wire nut. Usually you're not going to see that. Typical wire nuts, they come in different colors to indicate different sizes. 3 wires inside a wire nut is probably about the biggest that you normally see. If you see 3 of them, what that tells you is that either one of those is a source of electricity and the other 2 go out and distribute that. Distribution or distributing is a keyword of parallel circuits. The other alternative is that 2 of those have the power coming in and 1 is returning it back to the neutral. That would probably be a difference between whether you see 2 black wires or 3 black wires under a wire nut, which means power is coming in and then it's going out to 2 different load devices, Or you see 3 white wires under the wire nut, which means the power is returning to neutral from 2 of them and going back out through 1 wire back off to your panel. If inside of a junction box, a wire splits into 2, there's probably going to be a junction box, it may even be the same one, where the 2 wires come back together to give us 1 wire set back to the panel. The reason for doing this is simple cost saving. Why would we run 6 or 7 wires from the panel, which is possible? We could stick 6 or 7 breakers, each with their own light and their own switch, all out to a box, and then they each get their own switch, and then we send them off to their own lights. It's possible. But that would be incredibly cost ineffective, extremely expensive to do that. Not only the cost of the wires, the cost of the switches, the extra breakers, the size of the panel that you'd need. So instead, we come from a circuit breaker and come to a junction box, and then we split off from there, which means that if this is the case in a parallel circuit, we're going to see a wire nut with at least 3 wires underneath it. If you see that, you know that the configuration is parallel. But I suppose that kind of goes without saying, because if you see a house, you know that all the devices are in parallel. So it's kind of a giveaway that if you see 2 light bulbs, you would not guess that those 2 light bulbs are in series with each other. They're in parallel. Now, if it's a specialty light fixture, like if they've created a fixture with built-in LEDs or something like that, then it's very common or very likely that those might be in series in order to save power. But those wouldn't be light bulbs that you can unscrew the light bulb and just screw a new one back in when it goes out. Those are always in parallel, which means you always see the print on the top of the light bulb and it says 120 volts. So you know that those devices must be in parallel with each other. Now move on to industrial devices. So residential, wire nuts, very common. Every time you pull open a box, you're probably going to see wire nuts inside of there. But if you open an industrial control cabinet, at least one that's somewhat properly designed and maintained, you probably don't see a lot of wire nuts. Why? Well, wire nuts, they have a spring inside of them that as you tighten it more and more, the spring tightens down on the wires and binds them together. And when you unscrew it, you actually see little lines kind of gouged into the copper. It's supposed to be that way, and it keeps things all tightly connected, but it's not extremely vibration resistant. It doesn't take a whole lot of force to just back the thing right out. And if for some reason, in a house this isn't really going to happen because your house isn't supposed to be vibrating a whole lot, but if that were to happen, the wire nuts are quite likely going to fall off. And as soon as wire nuts fall off, then a black wire touching the side of a box, that can create a grounding issue, which means that it touches something that's connected to ground, and if we don't have a proper ground wire applied, then all the metal that's attached to that is now sitting with 120 volts waiting for you to touch it. That could be extremely dangerous. So instead, first we make sure that everything's properly grounded, but we also don't really have to worry about vibration in a house. An industrial machine, however, a control cabinet that's mounted right to a machine, vibration is going to be a big deal because every time you have a motor running, it's going to create vibration, at least a little bit. So instead, we focus on some different kinds of devices. Now, in an industrial setting, we tend to see these kind of devices in control cabinets a lot. This is called a terminal block. Now, terminal blocks can come in long sets of these terminal blocks all stacked up together, a bunch of them side by side, and we call that a terminal strip. Terminal strips can have a lot of different looks. This particular one is what we call a double level, which means that you see 4 pieces of metal, and if you follow the wire trace, all 4 of them are connected together. So if I run a wire into this top level, let's say it's a power wire. So I send 24 volts into this top level. Now this one has 24, this one has 24, and this one has 24. So I can feed 3 different devices from this one terminal block. Some terminal blocks are what they call single level. Single level means comes in on one side and only goes out one other terminal. That by itself doesn't seem really practical or useful because I can get power to here and then that power continues. Well, why not just use a longer wire if I could do that? First of all, it gives you a point to test. That's really handy in industry. In a household setting, you can probably get away with, if an outlet goes out, you can probably stand to have it go out either until an electrician can come and repair it and take a look at it, or until you can turn power off and take your time and remove wire nuts, things like that. But in industry, time is critical. So we want to be able to have easy access to testing things. But we also, to make it more practical and useful, we can also apply these things called jumpers. Now a jumper acts exactly like a like a wire nut in an outlet. Except that these ones will be one of two types. They will either, if you take a look at this one, you notice that right here, there is a little metal pad that's screwed in and it's jumping across. That's why they call it a jumper, because it jumps across both of these two terminal blocks. So before, I had 4 things all connected together, 4 terminals. Now with this jumper, I have 2 blocks of 4 terminals, which is 8 total terminals that will all be connected together with each other. So if I send power into one of those, I've used up one, it gives me 7 different places left over that I can get that power from. Now, since things are going to be connected in parallel, that means that I could send 7 different load devices their appropriate power as soon as I energize that one wire. So if I have a button that maybe needs to turn on 7 different devices, can't think of what that might be. That's a lot of different devices to turn on. But say we wanted to turn on 7 different devices. I push the button is connected to the terminal strip. This set of 2 terminal blocks jumpered together gives me all 7 of the wires that I need to distribute, which is why we call it distribution, to distribute the power to the other 7 load devices that are required. So this is a screw down terminal block, and we have to be aware of proper torquing, because when this is tightened down to the appropriate torque level, it withstands vibration. So even if the machine is vibrating, this does not work itself loose because we've followed proper torque specifications. If you torque it down way too much, the screws holding this thing down, they're not that beefy. So we can't just take a big screwdriver and just tighten it down because it'll strip all the threads out. We also don't want to tighten it down too little because then it might vibrate and fall back out, and then our jumper is lost. And then why do half of our load devices not work? Oh, it's just because one jumper fell out. So another type of jumper is, here's an example of one. They aren't always orange like this. They come in lots of different colors. But this one is, it's not a screw down. If you look at the top of it, there's no screw terminals on this thing. It is meant to simply be pressed down into a set of 2 side-by-side terminal blocks. Press it down, and in place you hear a click. Every set of terminal blocks requires its own type of jumpers. So we can't just buy a bunch of jumpers and say, oh yeah, this will work for everything, because it won't. There's certain jumpers, certain terminal blocks are going to require certain jumpers to go with them. So with this style, we simply press it down in, or we buy one that's a little bit longer and clip it off to the number that we need. Power distribution. Sometimes on schematics, you'll see it abbreviated PDB, stands for power distribution block. And those can be two different factors. They can be either a power distribution block is one giant hex-keyed lug that tightens down on a huge wire, and then on the other side of it is a whole bunch of other holes with hex-keyed, tightened down set screw lugs, and that's made for massive power distribution. However, power distribution for control systems, lower voltage, usually doesn't need to be huge screw down terminal lugs for carrying 50 to 100 amps. They're meant for carrying a few milliamps, small circuits. So we can get away with these small terminal strips that have a bunch of jumpers placed inside of them, and now 24 volts gets sent into it, and 24 volts can get sent off to hundreds of different devices if we need it to. So that's the parallel device. Now the cool thing about this is that no matter whether that's a household switch, a household circuit, or it's an industrial type of device, and whether it's load devices, which is the light bulbs, the relays, the indicators, things like that, or whether it's the control devices, which is the switches, the wire nuts and power distribution and terminal strips work for every one of those situations. So that means we can get we can use these wire nuts and terminal strips to send power to as many different devices as we need. There's a few things that we have to keep in mind, though, when it comes to parallel circuits. The fact that a parallel circuit can send power to as many different devices as we want it to seems too good to be true. It kind of is if we forget about the capacity of the supply that we're sending. Now that's 2 things. It's either the capacity of the power supply itself, scoot all the way back to episode 1 where we talked about power supplies and the limit of power. For example, a 60-watt light bulb. If you have a certain wattage output of your power supply, there's only a certain amount of power that you can consume. So if we have a power supply that can only send out, let's say, 30 watts. I have a bunch of DC power supplies, little 1.25 amp DC 24 volt power supplies, and they only send 1.25 amps, that's 30 watts, which is fine for a lot of stuff. But if I wanted to run light bulbs with it, let's say I got a light bulb that was rated for 24 volts, but it was a 60 watt light bulb, just like regular light bulbs, just rated for 24 volts, I would not be able to run that. In fact, as soon as I plug that light bulb in, it needs to consume 60 watts. My power supply can only provide 30 watts. So hopefully my power supply just shuts itself off or it burns up. That means that I have exceeded the power output of my power supply. Sometimes power supplies are not rated by their power, but rather their current. Current is a really important thing to know because I have to look at, in every device, how much current is it using at that particular voltage. If things have been stepped up and down, like you plug a cell phone charger in, and you say this is a 1 amp cell phone charger. That's pretty common to have a little USB module plug-in thing that says 1 amp out of it. Well, that's 1 amp at 5 volts. I look at the input and I say, okay, how much is it actually using at 120 volts? It's going to be far less, like 10 to 15 times less current usage. So it's going to be like 100 milliamps, maybe a tenth of an amp instead of 1 amp, maybe even less than that. So to look at a power supply unit, just like your breaker box at home, you'd have to look at how much current can I supply total before I start running into problems. The breakers are only designed to keep you from overheating things. The breakers are a safety, a fail-safe. They're only designed to trip in case of something exceeding the amount of total current capacity. So if we pull a lot of current through a circuit, you plug in too many of those 60 watt light bulbs, the power output will cause a current draw of too much current, and eventually you plug in one too many lights and the breaker trips. Don't replace the breaker with a larger breaker. The reason you don't want to do that is because all of the wires that are feeding that parallel branch are all the same size. All of the individual wires going to each one of those different branches, think about it like a ladder. Like a ladder has a bunch of rungs. If you run one wire into one side of your ladder, every rung can have a light bulb on it. And then from the other side of your ladder, it continues back off to ground. And that's all fine. Every one of those branches is only using 60 watts. Its wires are just fine. It's the wire that's coming into the branch and the wire that's going back out of that branch, the whole circuit, that's where you're going to run into problems. Every new load that you attach in parallel increases the total current consumption or total power usage of your circuit. So if you just start indiscriminately loading in load devices and putting more and more and more of these 60 watt load devices, they're going to pull too much current, and that one wire that's feeding everything and then returning us back to our neutral line or ground if it's in DC, that wire is going to start overheating. Overheating can cause fires. Pretty obvious why we'd want to have some sort of device that protects us against house fires. That doesn't take a whole lot of explanation. So that's what the breaker is there for. Now, if we switch to new load devices that consume less current and use less power, we're going to be safer all around because the device is consuming less power. So in most devices, as long as you're getting what you need out of it, but you can still get less power, that means that a lot of that extra power was probably heat. So we're reducing the amount of heat in the load. That's a good thing. We're also decreasing the amount of current total through the whole circuit. So our wires are running a little bit cooler. That's good. Our breakers aren't going to be as stressed out. So that's good. So it sounds like overall, if we can replace load devices with ones that use less power in parallel, we're going to be safer all around. And that's accurate. Just the one thing we want to be careful of, I guess, is cost. We don't want to just use too much money, spend a ton of money replacing every load device with something that's a little bit more efficient. But oftentimes now we don't have a whole lot of, there's not a whole lot of options available. So if all of the options available for all of our load devices happen to be very power efficient, great. That means the power company is going to be a little happier. Your power bill is going to be a little happier. Your wires in your house are going to be a little happier. If you have wires where, like, if somebody rewired your house and they tried to save a little bit of money and used wires that are a little bit too small, be really careful about that. Because when wires are too small, even just one gauge size different, that can cause a lot of extra stress. And all you need is just then somebody just plugs in one light bulb too many, and it may not be enough to trip the breaker. It may just be enough to really overheat that wire and the appropriate size of the connections. That's when we run into problems. The breaker somebody used an appropriate size breaker, a 20 amp breaker, that's fine, but the wire that they used was only rated for about 15 amps. So they started pulling 18 amps through it. Well, the breaker's fine, the wires are not. So the whole length of that wire, especially the connection points, are starting to get real hot and likely catching on fire. So make sure that if you're doing wiring in your house, or if you're having somebody rewire your house, just make sure that they're using the appropriate size wire, because you can save a little bit of money, but anytime you save money by cutting corners, you have to be really careful and you really need to know what you're doing. Otherwise, the cost for that can be, it can definitely be more expensive to have to replace your house, and just a lot more emotionally expensive if you have a house fire than simply using the right size wire for this one circuit that you needed replaced. Especially if it's just a little short length of wire, you really don't have any excuse, and you don't want to have to look back at that and say, I wish I had just used a slightly larger wire for this one circuit. You never want to be in that situation. Now, we talked about wire nuts and the terminal blocks with the jumpers on them. There's one other method that we may see somewhat commonly used, but I would say commonly used a little bit inappropriately, and that's to have, if you have screw terminals, this is especially common in industry, when things are tightened down with screw terminals, and you have multiple wires underneath a single screw terminal. If that's the case, then it also tells you that power is being sent somewhere else. Here's an example. Here I have a contact block from a switch, and on one side I have one wire, on the other side I have two wires. So what this would tell me is that power is coming into one side, and then it's coming out ground the other side. Now, it could be going off to another load device, or it could be going off to another distribution point, but whatever it is, I've got two wires underneath the same screw terminal. Two main reasons why I don't really like that method. Why it technically works, because all three of those wires, just like the wire nut making a connection, all three of those wires are going to be connected together. So it's all right, but two problems. The first one is, what if I needed a third wire connected there instead of just two? There's really not much I can do. I cannot cram another third wire underneath there. I simply don't have room to get a third wire under there. So I would have to then rearrange my entire system, go find a terminal block, some spare terminal block somewhere nearby, run a wire to that terminal block and run my two wires into the terminal block, and then add my third wire that I needed now to run back to the light, which uses an extra wire, and so I have to make an extra wire. I'm going to have a lot of downtime on that machine while I'm just adding another wire. If I had done that from the beginning, this is simply a matter of, while the machine is still running, I don't have to disconnect anything, I don't have to take apart screw terminals. I simply go make my right length of wire, attach it into my device, put it into the appropriate terminal block next to the terminal blocks where these are connected, and then stick my jumper in place. And the connection is done. There was no machine downtime needed. So do it the right way first, and then you don't have to worry about, well, I need another place to jam a wire underneath. Just, what do? There's nothing you can do. Here's the other reason I don't like these. Now, you notice here on these little devices, they're called ferrules. They crimp around the end of a stranded wire, keep you from having loose ends spreading out over asking to make contact with other things next to it. It's just a lot easier to deal with those, easier to tighten them down. But this one has two different sizes. Now, the black one is a little bit bigger gauge size. So you see if I wiggle that wire, it doesn't really move. The wire moves, but the black base doesn't really move. The white one, the base itself is moving. In fact, I bet if I just gave enough force, it's going to come right out. I did torque that one down pretty well. But what that means is the black one was a little bit larger gauge size than the white one. So when I tightened it down, which one is it going to tighten down on? Well, it's going to tighten down on the bigger gauge wire. Wire nuts don't tend to have that problem because you can bond a smaller one to a larger one. That's fine. It tends to twist them together. But when we deal with trying to cram two things under a screw terminal, we really have to assume, which is always a terrible thing in electronics, is assuming that things are going to work, but we have to assume that it tightened down equally on all of the wires in that bundle. If each one gets its own separate screw down, like it does with a setting on a terminal block, every wire gets its own screw terminal. You can tighten down every one of them and properly torque it down no matter what size the wire is. it's going to be way better, way more accurate in the long run. So there's a lot of ways to indicate that we have a parallel circuit: wire nuts, terminal blocks with jumpers making terminal strips, and sometimes seeing multiple wires, at least 3, stuck under the same place. And on a schematic, that would be shown with a wire and then another wire coming up to it, a T. Sometimes the T will come sideways and then branch off in 2 different lines. Later on, I'll talk about schematics and show you ladder schematics, which is a common industrial way of representing things. But if we see junctions in a schematic, then we know that parallel circuits are present. Control devices can be in parallel. Load devices can be in parallel. Those are much more common to be seen in residential and industrial settings. Load devices in series is more common in the small scale circuits where we're okay with getting a different voltage to every device. That's not usually the case in industrial settings. So there's very specific needs to look at each configuration of circuit based on the context of the circuit that you're looking at, based on the industry. So I hope you've enjoyed this one. Again, a little bit of a fresh twist on parallel circuits. Not going to spend a lot of time rehashing the same circuit diagrams that you can see in any textbook. Go look at those if you want. But take a look at and just think about how parallel and series circuits can really affect the way that you see things, because we're going to be running into those a lot as we look at control systems later on. Now, this has been kind of equally applied to both load and control, but as we focus on one or the other, we'll say things like, this is an appropriate one to use in series or not an appropriate one to use in series and in parallel. So I hope you've enjoyed this video. Stay tuned for more. There will be a lot more good stuff coming. We're still, again, only kind of scratching the basics of circuits after we looked at the basics of the necessity of a circuit. This is configurations, but we'll be moving to more specific stuff later on. As always, if you have any questions, ask away. I'd love to answer them if I can. And as always, go build something cool.